Another type of infinite series that we often work with is something known as a geometric series. We've actually already seen one of these in an example in the previous video, but a geometric series is of the form beginning at n equals 0, and that is relevant. Its terms are of the form a times r to the n, so that when n is 0, we have simply a, because anything to the 0 power would be 1. And then we have a times r to the first, and then a times r to the second, and then a times r to the third, and so on. The two parameters in this, a and r, have some interesting restrictions on them. First, and perhaps fairly obvious, is that a is not allowed to be equal to 0. It's not that a explicitly can't be 0, but if it was, every single term in this series would be 0. So we essentially wouldn't be adding anything up at all. So if a was 0, we would have a very unique and, quite frankly, very boring situation. On the other hand, r has a restriction that you might not expect, or rather a lack of restriction. Now you may recognize the form of this a times r to the n as being exponential. It has a constant multiplier in front, the a, but the exponential aspect of it is r to the n. So we have a constant base raised to a variable power. In continuous exponential functions, we had a restriction on the base that the base needed to be a positive value, and we did not want it to be 1. And the reason we didn't want it to be 1 is very much the same reason why we don't want a to be 0 here. Namely, that it produces a, frankly, boring situation because 1 to any power would be 1. However, the other really big and important restriction was that we could not have a negative base. Now, the reason for that is that in a continuous exponential function, the exponent can take on any real number, which, as long as the exponent was an integer, was not a problem. It became a problem when we had fraction or decimal exponent values. If our base was negative and our exponent was a fraction with an even denominator, such as 1/2, fraction exponents, remember, are the same as radicals. So in any even denominator exponent would turn into an even indexed radical, which tends to not work so well with a negative number. So in order to avoid that, we prevented the base from being negative by saying the base had to be greater than or equal to 0. I'm sorry, greater than 0, strictly greater than 0, and not equal to 1. However, we don't have that same problem here because we're dealing with discrete situations. The exponents here will only ever be integers, and typically positive integers, with the exception perhaps of the 0. But regardless, as long as the exponents remain integers only, then the base can be negative, and we would be able to evaluate it with no problem. So as it turns out here, r can be any real number, including 1 or even negative 1. Now, we tend not to let it be 0 because of the same situation that we have if a was 0. If r was 0, we would have 0 to any power is equal to 0, and it would wipe every term out, except the very first term. Because 0 to the 0 power is an indeterminate form. So we want to avoid that happening. Since n begins at 0, we don't want our base to be 0 to avoid that indeterminate form in the first term of the series. So the restrictions here are, like with an exponential function, are meant to make sure that we can actually evaluate each term of the series and therefore actually evaluate the sum. Now I mentioned geometric series follow very distinct rules for divergence and convergence. In fact, if the base, the ratio as it's called, is greater than or equal to 1, then the series diverges. On the other hand, if the base or ratio is smaller in magnitude than 1, then the series converges, and furthermore, converges to a very particular value, a over 1 minus r. So they are quick and easy to tell if they diverge or converge simply by looking at the value of r. And if it does converge, it is actually very easy to find the value to which it converges. We will go through a proof to show each of these situations, and it will take place in 3 stages. First, we're going to look at what happens when r is equal to 1 in magnitude, meaning it can also be negative 1. The idea is that we will use the absolute value of r. We will look simply at the magnitude of r, not worry about the sign. Because when it comes to the sequence of partial sums, if the sequence converges with all the same sign, then if it diverges when they're all the same sign, then it will definitely diverge when they are opposite signs. So in the case of r being equal to 1, our series is a times 1 to the n, which means our first term is a, and our second term is a times 1 to the first, and our third term is a times 1 to the second, and then a times 1 to the third, and so on. So that the partial sum of the first n terms will simply be n a's added together. And of course then, the limit as n goes to infinity of n times a is going to be infinity regardless of the value of a. If r was negative 1, then what we have here is, we've seen this before, we have an alternating sign. So that when n is 0, negative 1 to the 0 is 1. And then when n is 1, we have negative 1 to the first. So we end up with a times negative 1 is negative a. And then we have negative 1 to an even power, a and negative 1 squared. And then negative 1 to an odd power, negative 1 cubed, and so on. So that our partial sums are going to alternate between a and 0. S sub 1 would simply be a. S sub 2 would be a plus negative a, which is 0. And then S sub 3 would introduce another a. And then S sub 4 would introduce a negative a to cancel that out. So in this case, the series diverges because the sequence of partial sums does not approach a unique value. These partial sums alternate between a and 0. So in the case of r equals positive 1, the sequence of partial sums approaches infinity. Therefore, the sequence does not converge, and therefore the series does not converge. In the case of -1, the series does not approach a unique finite value, and therefore the sequence of partial sums does not converge, and therefore the series does not converge. Next, we will talk about when the magnitude of r is greater than 1. Now, the trick to this is to realize that when you take a value that is larger than 1 and multiply it by itself, the result is larger than the value you started with. So when we square r, it will be larger than r by itself. And then if we multiply by another r, that will be bigger still. And then if we multiply by another r, that will be bigger still. The idea then is that each new term is larger in magnitude than the term before it. And if we continue to add numbers that are larger in magnitude than the one before it, we get an ever increasing sum. The idea is then that s sub 1 would simply be equal to a, s sub 2 would be equal to a plus a times r to the first. Of course, a times r, since r is bigger than 1, a times r is bigger than a. So this is bigger than 2a. S sub 3 then r squared is bigger yet. So if r, multiplying a by r results in a bigger value than a, multiplying a times r squared results in an even bigger value. So this is bigger than if we just had 3 a's put together. In general, the nth partial sum is going to be bigger than n times a. We already know that the limit as n goes to infinity of n times a is infinite, which means that the nth partial sum also approaches infinity. And thus the series would diverge. It's not that hard to show that if r was negative, that we would simply end up with an alternation of the terms, but it still would result in the same thing. For our third situation then, when r is smaller in magnitude than 1. In this case, we're going to look at two things. First, the partial sum of the first n terms. Now remember, the series begins at 0. So the first n terms will end at the n minus 1th power of r. Now, with a little bit of creativity here, I'm going to take this equation and multiply both sides of it by r, so that what I have here is r times s sub n. When I distribute the extra factor of r on the right side, all it's going to do is increase the power of r on each term by 1, because it's simply introducing one more factor of r on each term. this results in the last term of my partial sum now being a times r to the n. I'm now going to take these two things, s sub n and r times s sub n, and I'm going to subtract them. And the reason I'm going to do that is because s sub n minus r times s sub n has a common s sub n in it. So when I combine these, I will get something that will allow me to isolate s sub n, which ultimately is the goal. Now, s sub n is a plus a times r plus ar squared plus ar cubed up to a times r to the n minus 1. And I'm going to subtract from that r times s sub n, which begins with a times r, and then ar squared, and then ar cubed, ending at ar to the n. And what I have here is that the interior terms, similar to a telescoping series, all cancel out, and the only terms that don't have something to cancel out are the a at the very beginning, and after distributing the negative, a minus a times r to the n, which can have a common a factored out. The last step of this then is to get s sub n by itself. I can divide both sides by 1 over r. Excuse me, by 1 minus r, excuse me. So I now have s sub n is equal to a times 1 minus r to the n over 1 minus r. To show convergence then, we would need to do the limit as n approaches infinity of s sub n, which is a times 1 minus r to the n over 1 minus r. The interesting thing about this is that a is constant in terms of the limit because it is not dependent on the value of n. 1 minus r is also constant in terms of the limit because it also does not depend on the value of n. The only thing that does depend on the value of n is this factor of 1 minus r to the n. So in terms of the limit, the a in the numerator and the 1 minus r in the denominator, being constants in terms of the limit, can be brought out in front of the limit. Now, of course, the limit of 1 is 1. So what we really need to look at is the limit of r to the n. But what we also know here, much like we saw when r was bigger than 1, when r is smaller than 1, r squared is actually going to be smaller than r to the first. And r cubed is smaller yet than r squared. Because when you take a value smaller than 1 and multiply it by itself, it gets even smaller. Take 1/2, for example. If I multiply 1/2 by itself, 1/2 of 1/2 is 1/4, definitely smaller than what I started with. And then if I multiply by half again, I now have half of a fourth, which is an eighth. And then half of an eighth, which is a 16th. And I'm always cutting it in half, thus making it smaller. So the idea here is that as n goes to infinity, r to the n is going to approach 0. So what I'm left with is a over 1 minus r. Thus, the series converges to a over 1 minus r, provided r is smaller in magnitude than 1. Please note that at no point here did we need to distinguish between a positive r and a negative r, since the terms in s sub n minus r times s sub n all canceled out because they are the same terms, regardless of whether r is positive or negative. So no point in the algebra here, at no point in the algebra did we need to distinguish between r being positive or negative. Now, I mentioned earlier that we had seen previously a geometric series, and that series was from n equals 0 to infinity of 1 over 2 to the n, which we already saw converged to 1. We also saw how this can be written as a geometric series. Excuse me, the original series began at 1. For a geometric series to work, it must begin at 0, which simply means that we would end up with 1/2 as our coefficient times 1/2 to the n. This would allow us, when n equals 0, to still begin the series at 1/2, and then when n is 1, to get 1/4, and so forth. So we would end up producing the same terms. This, however, is in the form of a geometric series where a is equal to 1/2 and r is equal to 1/2. According to the sum of a geometric series, then, this should be equal to a over 1 minus r. Of course, in the denominator, 1 minus 1/2 is 1/2, and 1/2 over itself is equal to 1. So in the prior example, by defining a formula for the nth partial sum, and now using the geometric formula, we get the same results. Of course, both a and r being the same exact value, perhaps that makes it perhaps a little too obvious. Maybe this is just a little too coincidental. So let's look at another example. Something perhaps less obvious. Let's consider the sum where a is 4 and r is 2/3. Now, according to the geometric series, this should be equal to, because r is 2/3 and that is less than 1, this should converge to a, which is 4, over 1 minus r. 1 minus 2/3 is 1/3. And therefore, this should converge to a sum of 12. Now again, this is not necessarily the most obvious thing. So let's apply the original technique of defining s sub n. So let us begin with s sub 1, which would just be 4, because 2/3 of the 0 is 1. S sub 2 then would be 4 plus the second term of the series, which would be 4 times 2/3 to the first, or 8/3. This would result in 20 over 3. S sub 3 then would be the 4 plus the 8/3, plus when n is equal to 2, 2/3 squared is 4/9. Times 4 would give us 16/9. Now we already know that 4 plus 8/3 is 20/3. So to add 20/3 and 16/9 would require the common denominator of 9. That would give us 60/9 plus 16/9 is 76/9. S sub 4 would be 4 plus 8/3 plus 16/9. And then we would have 2/3 to the third power, which is 8/27. Times 4 would give us 32/27. Now we know the sum of the first three terms is 76/9. To get a common denominator, we would have to multiply 76 and 9 each by 3 to get a denominator of 27. And that would give us 228/27 plus 32/27 is 260/27. So these are the first four partial sums, and admittedly, they are not obvious. Through some careful pattern recognition, we can realize that first, the denominator always seems to be a power of 3. Specifically, a power of 3 that is 1 less than the number of terms that we're using. The numerator is less obvious. However, as it turns out, the numerator is equal to 4 times 3 to the n minus 2 to the n. Not obvious, but it's there if you wish to go through and verify that. So what we would need to do now is find the limit of that expression. Now perhaps it would be easiest to get that 4 out of the way. It is constant in terms of the limit, so we can simply bring it out in front. The other thing that might help here is to realize that we have a numerator that is 2 terms and a denominator that is a single term. So perhaps it would be best to distribute that denominator underneath each. The advantage here is that in the first of those terms, we're looking at something with the same base. Something with the same base where the numerator will always have one more factor than in the denominator. We can write that as 3 times 3 to the n minus 1 over 3 to the n minus 1, so that we get those canceling out, and we would just be left with a term of 3. Now, we can do something similar in the second term, in the sense that if we recognize that the exponent in the numerator will always be 1 greater than the exponent in the denominator, we can write this as 2 times 2 to the n minus 1 over 3 to the n minus 1. Now, while we don't get any canceling like we did in the first term, we can realize that since the n minus 1 exponents are the same in the top and bottom, we can rewrite that term as well. So we now have our 4 out in front. We have the limit as n approaches infinity of 3 minus 2 times 2/3 to the n minus 1. Of course, the limit of 3 is 3. But as we already talked about from the proof of a geometric series, if we take a ratio that is smaller than 1, like 2/3, and let its power approach infinity, then each thing will get smaller than it was before. 2/3 of 2/3 of 2/3 of 2/3 means we're going to keep getting smaller. So even though we have the 2 in front of that, the 2/3 raised to an ever-increasing power is going to approach 0. Which means ultimately what we're left with is just the 4 times the 3, which is 12. Exactly like the formula that the geometric series gives us. I think you can agree, though, that the formula is a over 1 minus r is considerably faster than what we did here. And that numerator, 4 times 3 to the n minus 2 to the n, is not an obvious expression to come up with. So certainly this is not the most obvious thing. The geometric series formula, a over 1 minus r, is certainly better. Now, one particular use of geometric series, interestingly enough, is to convert repeating decimals back into fractions. The idea is that a rational number, which has two definitions, one using fractions and one using decimals. A rational number is a number that can be written as a fraction of integers, where the numerator is an integer and the denominator is an integer. The other definition is that it is a terminating or repeating decimal. This means that any terminating or repeating decimal can be written as a fraction of integers. Now, in some cases, it's obvious. If you have something like 0.328, this is simply 328 over 1,000. We can take the finite number of decimal places, and based on whichever place value the last one is in, we can determine the denominator. In this case, 8 is in the thousandths place. Hence, our denominator is 1,000. But it is also possible to write repeating decimals as in a fraction form. We know that, for example, 1/3 is equal to 0.3 repeating. But suppose we start with the decimal form 0.3 repeating, how would we know that that produces the fraction of 1/3? Unlike the terminating decimal, there is no last decimal place from which to pull the denominator based on its place value. The trick here is in a geometric series. For example, let's choose something perhaps a little bit less obvious. Let's pick 0.080808, etc., also known as 0.08 repeating. The trick here is to realize that we can take our repeating pattern, and each separate bit of this can be written as its own fraction, much like I did with the 0.328 up above. The first 0.08 is 8/100ths. The next 0.08 is 8 in the 10,000ths place. The next 0.08 has an 8 in the 1/1,000,000th place. Etc. Now, this may not look like much until we realize that each denominator is a power of 10. 100 is 10 squared. 10,000 is 10 to the 4th. 1,000,000 is 10 to the 6th. And in this way, the pattern becomes a bit more obvious. If we look closely, though, this is a geometric series where the first term is 8 over 10 squared. And then each other term is the exponent is now doubled in the denominator. So if we allow our series to begin at n equals 0, and we have our denominator be 10 to the 2 times n plus 1, when n is 0, we will get 10 to the first. When n is 1, we will get 10 to the 2 times 2, which is 10 to the fourth. When n is 2, we would get 10 to the 2 times 3, or 10 to the sixth, and so on. Now, of course, this is not exactly in the right form for a geometric series. We need to do a little bit more careful manipulation of this here. So what we can do is take our individual terms and factor out some common things from them. They all have an 8 in the top. So I can factor that out from all of them, and that would leave me with a 1 in the top of each one. Now, as for the denominator, I need to get my first term out as my a. So I'm going to draw a 10 squared out of each of these, which means if I draw a 10 squared out of the first denominator, I'm left with just a 1. If I draw a 10 squared out of the second denominator, I have the other 2 10s, and then the other 4 10s, and so forth. So this gives me my a as 8 over 100. For the others, then, the first term is basically 1 over 10 to the 0, and then 1 over 10 squared, and then 1 over 10 to the fourth, and so on. So that each denominator is 10 to the 2 times n power. Another way to write that is 1 over 10 squared to the nth. Finally, I can write this as 8 over 100 times 1 over 100 to the nth. This is my geometric series then. 0.080808, etc. is equivalent to the geometric series beginning at 0 of 8 over 100 times 1 over 100 to the nth power, which can then be, the sum can then be found using the formula a over 1 minus r. One minus 1/100th is the other 99 100ths. And since they have the same denominator, this really just becomes the ratio of the numerators. So 8 over 99 is the fraction equivalent, the rational form of 0.08 repeating. This can be applied to other irrational numbers as well. Other rational numbers with repeating decimal equivalents that maybe not every term of the and maybe not every digit of the decimal is repeating. For example, suppose I have 0.416 where only the 6 repeats. In this case, I start with 41 100ths, and then 6 thousandths, and then 6 10,000ths, and then 6 100,000ths, and so on. The idea then is that I can separate out the 41 over 100, since that is not going to fit the pattern of a geometric series, since it has a different numerator, and I can focus on just these other terms to define my geometric series. In this case, they have the common factor of 6. And in the denominator, I have powers that start at 10 cubed, and then 10 to the 4th, and then 10 to the 5th, and so on. So if I factor out the common 6 and a 10 to the 3rd in the denominator, that would leave me with 1 plus 1 over 10 plus 1 over 10 squared, etc. This then should be much more obvious as 6 over 10 cubed times 1 over 10 to the n, where n begins at 0. Of course, I do still have my separate 41 over 100 in front of this. But now I can use the geometric series formula to evaluate the geometric series and then add the fractions together. So my 41 over 100 is still sitting there. And then I'm going to have 6 over 1,000 in the top. And the denominator, I'm going to have 1 minus 1/10. Of course, 1 minus 1/10 is 9/10. And this is not too hard to work with. 41 over 100 to begin with. And then in order to resolve the complex fraction, I can change it from division to multiplication by the reciprocal. This will give me some cross simplification, including with the 6 and the 9. So now I have 41 over 100 plus 2 over 300. A common denominator then would give me 123 over 300 plus 2 over 300 for a total of 125 over 300. And then this can be simplified. Both of these are factors of 25. Dividing each the top and bottom by 25 reduces me to 5/12. So 0.416, where the 6 is the only repeating digit, is equal to the fraction 5/12. This can be easily verified with a calculator. One very big use of geometric series, therefore, is to show that repeating is to find the rational fraction equivalent of a repeating